Section 2.6, and we're talking about rational functions and asymptotes. So let's talk a little bit about what a rational function is. Did I say ratio? Like ratio? So that was a big hint there. So when we're talking about a rational function, what are we talking about? It has to do with the ratio. All right, we got that. Ratio of, what is a ratio? What's another way we can say ratio? Division, fraction. Has to do with fractions or division. So we're making a fraction. So a rational function is going to be a fraction. And we're talking about functions, so what kind of functions do you guess we're making a fraction out of? What kind of functions have we been talking about for the whole unit? What is it? Someone said some quadratic is one type of function, this type of function. Polynomial, very nice. A fraction of polynomials. We've spent all this time figuring some things out about polynomials and how to work with polynomials. So rational function is a fraction of polynomials. I'm going to write it for today. We're going to write it as f of x equals n of x over d of x. N for the numerator, d for denominator. So, and each of these is a polynomial. And we're going to do several things with these rational functions. We want to find one thing that we're interested in is finding the domain. So, whenever we have a fraction, what do we have to worry about when we're dealing with functions? Can't have a zero in the bottom. We can't have a zero in the denominator. So the domain of a rational function is going to be where d of x not equal to 0. And be careful here. A lot of people get confused. They find where the denominator is 0 and say that is the domain. That's the domain restrictions. The domain is where the denominator is not equal to 0. So it's an easy one to make when you're just thinking about it really quickly. So we need to figure out where the denominator is not equal to 0. Well, our domain restrictions are going to be where the denominator does equal 0. How do we find where the denominator equals 0? The denominator is a polynomial. We have to find the zeros of a polynomial. What have we been doing for almost the entire unit? Finding zeros of polynomials. So we have to find zeros. So what are our tools for finding zeros of polynomials? P's and Q's, factoring, synthetic division, long division. That's what we've been doing for the entire unit almost, is finding zeros. So that's one reason we're talking about rational functions in this unit, is because part of what we have to do with rational functions is find zeros of polynomials. X-Intercept. So where am I going to find an X-Intercept? Just for functions in general, where are the X-Intercepts? Where y is 0, right? And when we use function notation, we're going to say f of x equals 0. Well, what's going to make this fraction, this rational function, what's going to make this fraction equal to 0? When the top equals 0. The x-intercepts are where n of x equals 0, where the numerator equals 0. The numerator is a polynomial. We find where the numerator equals 0 with the same tools that we've been using all chapter. Synthetic division, factoring, long division, P's and Q's. So again, we're back to setting our dumpster on fire. Okay, we know how to solve that problem. What happens, going back to where we have a domain restriction, with the graph of a rational function? We've seen them before. What happens when we have a 0 in the denominator? What happens to the graph? What's that? No solution is undefined. So what does the graph do? What does it look like? There could be a hole. That's one thing that can happen. What else can happen? But bounce. So we get and let's think when we divide by 0, when we divide by a really small number, what kind of number we get? A really big number. So our graph is going to get really big, either positive or negative. So what do we call that when a graph gets really big, goes really steep, positive or negative? The hint is in the title of the asymptote. There we go. So let's look at a graph of a rational function, and we'll talk about asymptotes, and then we're going to talk about how we find them. So let me grab this and have it here. Take a picture. All right. So there's a graph of this rational function. 2x minus 5 over x minus 2. So the denominator equals 0 where? At x equals 2. And what's happening to my graph here at x equals 2? You get this strange thing happening. So if I draw a line there at x equals 2, like so, that's going to be my vertical asymptote. So x, as x gets close to 2, we're dividing by a really big number. On this side we're dividing by a really big negative number. So our function gets really big negative, or really small negative number. Sorry. And so f gets really big, and over here we positive, so f gets really big in the positive way. Is there another place on the graph where it looks like our function is getting really close to it? What's that? A horizontal asymptote. We have a horizontal asymptote here at y equals 2. So let's draw a line in there. So like so. So we have this line here, y equals 2, that our graph is getting very close to as x gets very large. So as x comes out here to positive infinity or negative infinity. So that's our horizontal asymptote. Rational functions usually are going to have some combination of vertical and horizontal asymptotes. There can be multiple vertical asymptotes. There's only going to be one horizontal asymptote. So a rational function is going to have some combination. The graph is going to look, it can either go up on both sides to our horizontal asymptote, it could go down on both sides, or it's going to do some combination of up and down, or down and up. And if we have multiple asymptotes, so we have some combination. If we have multiple asymptotes, our graph can do all kinds of crazy things. It can do this. And if we have an asymptote here, in between it might do something like this. It might do something like this. So we get all kinds of crazy looking graphs between with vertical and horizontal asymptotes. But we'll have some kind of combination. So we'll talk about what an asymptote is in a little more technical terms, and then we'll talk about how to find it. And that's really all we're interested in today, is how do we find it? How do we find the domain of a rational function? How do we find the x-intercepts of a rational function? How do we find the asymptotes? Tomorrow we'll talk about how we put that all together to make a graph of a rational function. All right. So a vertical asymptote. And I want to talk about it this way because we're going to connect what we're talking about today to something we'll talk about a little later. So we have a vertical asymptote. We're going to say the vertical asymptotes are always a line. X equals A is I'm just going to use VA for vertical asymptote. VA of our function if our function, and this arrow, it means approaches, plus or minus infinity as x approaches A. So we'll talk about this idea of approaching and what that means a little later. It has to do with limits. We'll talk about the idea of a limit. So if we look back here, as x approaches 2, my function approaches positive infinity. It gets really, really big. As x approaches 2 from this side, the function approaches negative infinity. It gets really, really big in the negative direction. So that's what this is telling us. Horizontal asymptote. And a horizontal asymptote is a line. Y equals B is I'm just going to use HA of F if f of x approaches B as x approaches plus or minus infinity. So the horizontal asymptote is telling us something about what happens to our function eventually. We get out really far to the left or really far to the right. What else have we called that? We've worked with that before. What do we call that for our function? It was on the quiz. The right and left hand behavior. The end behavior. So the horizontal asymptote asymptotes tell us about the end behavior of our function. As x gets really, really large, what's happening to our function? As x gets really, really small, really large, negative, what happens to our function? If I go back to this graph, as x gets really large, our function is getting closer and closer and closer to 2. That's the end behavior. Eventually it gets really close to 2. In this direction, eventually it gets really, really close to 2. It's telling us about our end behavior. And a little later, we'll talk about this idea of limits. These things in terms of limits. Limits of functions, extremely important idea in there. All right, any questions so far? Well, let's talk about how we find these things. We want to find our vertical asymptotes. We want to find our horizontal asymptotes. So we're going to talk about some rules. Vertical asymptotes are easy. I'm going to use VA And I'm going to say that, again, f of x equals n of x over d of x. That's our rational function. So we'll talk about numerator and denominator. Vertical asymptote. When do we get a vertical asymptote? When what happens? When the denominator and our vertical asymptote is always a line. So we're going to say x equals a when d of a equals 0. So when I get a 0 in the denominator, I make a vertical asymptote by the line x equals a vertical line. For the horizontal asymptotes, we have three different things that can happen. And our rules for the horizontal asymptotes depend on the degree of the numerator and the degree of the denominator. So when we're talking about the degree of the numerator and denominator, what are we talking about? What power x is raised to, and we're looking for, if we're looking at a polynomial, there's a bunch of powers. Which one are we looking for? The highest. We're looking for the highest power. So the degree of the polynomial is the highest power. So our first one, for a horizontal asymptote, and I'm going to use DEG for degree instead of writing down degree each time. If the degree of the numerator is less than the degree of the denominator, then y equals 0 is a horizontal asymptote. So if the degree of the numerator is smaller, then we get y equals 0 as a horizontal asymptote. Y equals 0 is the x-axis. And if we think about this based on how the function is behaving, so let's say the degree of the numerator is 2 and the degree of the denominator is 5. So as x gets really, really big, raising something to the 5th power is going to give me a much bigger number than raising something to the 2nd power. So I end up dividing by bigger and bigger and bigger numbers, so my rational function gets smaller and smaller and smaller and smaller, closer to 0. So that one's the first one. If the degree of the numerator is smaller, then y equals 0 is a horizontal asymptote. For our second one, and that second one is for horizontal asymptote also, if the degree of the numerator and the denominator are the same, then our line is y equals, and I'm going to write it out in words, the ratio of the leading coefficients. Is a horizontal asymptote. So what do we mean by the leading coefficients? The number in front of x, which x? In a polynomial we have a bunch of x's. A1, so the highest degree, yes. So the number in front of the highest power of x. So if I'll write just a quick example here just so we see what we're talking about. If we have 3x to the 5th plus 4x to the 4th plus ... And on the bottom we have 2x to the 5th plus 1x to the 4th minus ... Our leading coefficients are 3 and 2. So y equals 3/2 is a horizontal asymptote. So if our degrees are equal, we look at the number in front of the highest powers on our variable, and we say y equals 3/2 is a horizontal asymptote. Our last rule is kind of a non-rule. If the degree of the numerator is greater than the degree of the denominator, we have no horizontal asymptote. What kind of asymptote can we get in that situation? Slant. We can get a slant asymptote. We'll talk about slant asymptotes tomorrow. So in some situations we get a slant asymptote. So our end behavior is just a little more complicated, but we can figure it out. Since we're talking about fractions of polynomials, what would you guess slant asymptotes have to do with? We're dividing polynomials. Slant asymptotes have to do with long division. So we'll use long division to find slant asymptotes. So again, connecting to things we've already done. There's one thing that we didn't write down in these rules that I want to show in an example that we have to be careful of. So any questions on our rules? Not too much to remember. Vertical asymptotes are easy when the denominator equals 0. Horizontal asymptotes, we just have a couple of things to remember about how the degrees of the numerator and denominator are related. All right. Let's look at this rational function. We want the horizontal asymptote and the vertical asymptote. Now what we're going to do with rational functions when we're talking about these is the first thing that we always want to do is factor the numerator denominator as much as we can. We don't have to factor them with the complex roots, just with our normal factor. So if I factor this, x plus 1, can I factor the denominator? What does that factor to? X plus 1, x minus 1. Well, we have a factor of x plus 1 in the numerator and the denominator. What happens when we have a common factor in the numerator and denominator? We have a whole. So this tells us we have a whole at x equals -1. If we have a whole at a particular location, we do not have an asymptote there. All we have is a whole. I think of it as we're kind of crossing that number out of the graph, kind of xing it out. So we just have a whole, we don't have an asymptote. So -1 makes the denominator 0, but it also makes the numerator 0. So that gives us a whole, not an asymptote. All right, so let's look. We've got half of the vertical asymptote part figured out. So where's our vertical asymptote? When the denominator is 0. We figured out there's one place, but that's a whole. So where's the other place the denominator is 0? X equals 1. So there's our vertical asymptote. Our horizontal asymptote, how are the degrees of the numerator and denominator connected, related? The denominator is bigger, so what is our horizontal asymptote? Y equals 0. The degree of the denominator is bigger, so y equals 0 is our horizontal asymptote. And we'll talk about how to make a more accurate sketch, but if I sketch this really quickly, here's my asymptote at x equals 1. This function would turn out to look like this. And then over here, like so. And this goes over, there we go, that looks a little better. And then at x equals -1, we would put a circle in the graph. So we're not including that point. So that would be my hole. So first thing we want to do is factor everything completely. The place where we have a common factor in the numerator and denominator, that's going to give us a hole. The holes where we have a hole, we do not have an asymptote. Questions on that one? Yeah, let's look at one more. 2x plus 5 over 4x minus 6. And we want to find our vertical and horizontal asymptotes. So which one do we want to find first? Vertical, okay? Where is our vertical asymptote going to be located? When what equals what? When the denominator equals 0? 4x minus 6 equals 0. So x equals 3/2. So our vertical asymptote is at x equals 3/2. The horizontal asymptote, we look at how the degrees of the numerator and denominator are related. How are they related? The same. So our horizontal asymptote is going to be at y equals 2/4 or 1/2. Ratio of the leading coefficients. So that's my horizontal asymptote. Let's look at one more really quickly. The powers, the degree of the numerator and denominator are the same. So we look at the ratio of the leading coefficients. 2 over 4. So 2 over 4 is the same as 1/2. Just be 1. Because the degree of the denominator is larger than the degree of the numerator. The second degree in the denominator, first degree in the numerator. Okay? Yes? Yes. All right, last example, x squared over x plus 1. Vertical asymptote, where's my vertical asymptote here? X equals -1. Horizontal asymptote. None. The degree of the numerator is larger. There is no horizontal asymptote. Turns out that this particular rational function has a slant asymptote. And if I graphed it, it would look like something like this, just a quick sketch. So there's my vertical asymptote, and the graph does this. Looks like that. All right, are we all good on the rules? We have a slant asymptote. I didn't draw it really well, but we have a slant asymptote that goes along here. And we'll talk about how we find those. We'll talk about how we find those tomorrow. So our vertical asymptote is here, and this is our slant asymptote. All right, homework. All right, there you go.